Picture this. You've got Emma, a graphic designer who's right in the middle of a massive new project. A colleague mentions a tool that uses AI to create entirely new designs, images, and text from absolutely nothing. Now, Emma's naturally intrigued, right? I mean, she knows the basics of artificial intelligence, but she's wondering, how on earth can a machine mathematically generate something beautiful and highly specific from scratch? Her curiosity grows and she decides to dive into the technical mechanics of generative AI. Well, in this explainer today, we are going to take that exact same journey right alongside her. Here is our quick roadmap for today. First, we'll meet generative AI. Then, check out real-world applications. After that, we're looking under the hood, learning from feedback, and finally, exploring the power of originality.
Okay, Section 1. Meet generative AI.
So, for years, we've relied heavily on traditional, discriminative AI. That kind of tech primarily analyzes or categorizes existing data. It basically maps inputs to predefined labels. Think of a system trained to scan 1,000 photos and correctly label which ones have a cat in them. Generative AI, on the other hand, it shifts the paradigm entirely. Instead of just mapping to a label, it maps inputs to entirely new data distributions. It produces totally original content, like text, images, music, you name it. Based on complex statistical patterns it learned from vast datasets. It isn't just organizing data anymore, it's literally synthesizing new, unique material from a simple user prompt.
Moving right along to Section 2, Real-World Applications. The practical scope of these generative models across different industries is absolutely staggering. In content creation, large language models are writing essays, reports, even generating code from just a few words. In art and design, diffusion models are completely transforming visual creativity by generating incredibly high-fidelity images. In audio, AI is composing original music and mimicking vocal timbres. But perhaps most impactfully, and this is a huge deal, in healthcare, generative AI is creating synthetic medical data. This is a massive breakthrough because it lets researchers bypass the strict privacy bottlenecks of real patient data so they can simulate diseases and train diagnostic models way faster.
Let's dive into Section 3, Looking Under the Hood.
To really understand how Emma's graphic design tool actually works, we have to look at the neural network's architecture. It all kicks off with data collection. These models are trained on immense data sets, where millions of images are explicitly paired with text descriptions. During training, the network learns by mapping these inputs into what's called a multidimensional latent space. Basically, it's constantly adjusting its internal weights to recognize complex patterns, learning the visual geometry of a cat, the shape of sunglasses, and, critically, how to statistically link specific text to those visual representations.
And the absolute engine driving this text understanding is the transformer model. It's a real game changer. Let's say Emma types the prompt, "a cat wearing sunglasses." The transformer jumps right into action. Its core innovation is something called the attention mechanism. Instead of reading the prompt sequentially, like we do, the attention mechanism lets the model weigh the importance of different words simultaneously. It focuses heavily on the contextual relationship between cat and sunglasses, linking those concepts to the visual data it mastered during training. That's how it calculates exactly how to combine these distinct elements into one coherent output.
Actually, to be perfectly accurate, the AI doesn't read words at all. The input text is split into mathematical pieces called tokens. The model processes each token to calculate the exact semantic relationship between them. Because of how it computes the sequence for "a cat wearing sunglasses," the model inherently knows that the sunglasses can't just be floating in the background. Statistically, they need to be positioned directly over the cat's eyes. This mathematically driven context is the secret sauce that creates a highly accurate final image. Now, the infrastructure making all this possible relies on over 1 billion parameters. Yes, you heard that right, billions. These parameters are essentially the learned weights and biases distributed throughout the entire neural network. They act as the mathematical memory and decision-making fabric of the AI. When you enter a prompt, that request passes through these billions of interconnected parameters, each doing a microscopic calculation, ultimately guiding the generation toward that crisp, high-resolution result. All right, on to Section 4, Learning from Feedback.
But, what happens if the model messes up? Let's say Emma gets her image back, but the sunglasses are just awkwardly floating in the air next to the cat. Well, the system isn't broken. It just needs a little tuning. Emma can actually flag that specific generation as incorrect. This user feedback acts as a direct mechanism for the model to realize it failed in its contextual mapping, giving it vital data to improve future outputs.
This ongoing improvement is powered by reinforcement learning. Think of it like training a puppy. The model is computationally rewarded when it makes an accurate image, and penalized when it makes an error. When Emma gives that negative feedback, the system physically alters those billions of parameters, tweaking the weights and biases to mathematically steer the model away from making that same mistake again. On the flip side, if she asks for a sunset and gets a gorgeous, perfect image, positive reinforcement solidifies those neural pathways. It's constantly refining its precision over time.
Finally, Section 5, the power of originality.
So once this model is fully trained, it isn't just regurgitating things it's seen before. No way. If Emma prompts the AI to draw a futuristic cityscape, the output is a completely unique image. It is an entirely new creation, not just a copy and paste collage from a massive database. Because the model is navigating incredibly complex probability distributions within its latent space, it is creatively synthesizing its learned mathematical patterns into a visual structure that the world has literally never seen before.
To wrap up this explainer, let's distill everything back down to the core concept from our source material with a quick quiz. So, what does generative AI primarily do? Is it A, analyze data, B, generate new content, or C, store data? Take a second to lock in your answer.
And the answer is B, generate new content. Unlike traditional AI that just maps inputs to labels, this text maps inputs to entirely new creations. As we've seen with Emma's journey today, from crunching mathematical tokens and leveraging attention mechanisms to tweaking billions of specific weights through reinforcement learning, the mechanics behind this are just incredible. Which leaves us with one final, exciting question for you to ponder. Now that you know how it all works under the hood, what entirely new creation are you going to generate next?